for a long time. The switch in the circuit below was moved to position 2 at t equals 0. So it had been in this position for a long time, and then we need to find out these other things about it. Okay, so what I like to do is, regardless of what the problem is asking, I know that I'm going to need to find stuff at time t equals 0 and time t equals infinity. If it's an inductor, I'm going to need to find I through the inductor at 0 and I through the inductor at infinity. If it's a capacitor, I'll need to find V through the capacitor at 0 and V through the inductor at infinity. You're going to need that. If there's an inductor in the problem, you'll need that. If there's a capacitor in the problem, you'll need the voltages. Unless the problem just doesn't ask anything useful. This is not the one I wanted to do. I wanted to do number. Didn't I have one that didn't have a dependent source? It looks like I just didn't copy it. What is the second to last problem? Can someone? Yeah, I just had that one a minute ago. What did I do to it? Okay, so. And the inductor is 0.2, and R3 is 60, and R2 is 120, and R1 is 30, and V is 12, and we're supposed to find IL of 0 minus, VL of 0 minus. This just means right before 0. And IL of 0, and VL of 0, IL at infinity, VL at infinity, IL of t and VL of t. Okay, so at 0 minus, the switch has not been the switch hasn't done anything, right? Before 0? Is it in the bottom position? It was in this position? Okay. Okay, so that means that this part of the circuit's not doing anything. So before 0, it looks like this. So this makes before 0 easy. So before 0, what is IL of 0 minus? What's the current through that inductor? 0. What's the voltage across that inductor? 0, because there's no source. Okay, now let's look at infinity. So at infinity, we have it goes up to this position, right?
Yes.
No, that's 60. Okay, so at infinity, what is the current through that inductor going to be? What's the inductor going to act like at infinity? A wire.
So it's going to short out. The voltage will be at 30.
Yep. Which is 0.4, if I did that correctly. 0.4 amps. what is the voltage across the inductor at infinity? What's the voltage across a wire? 0. So if you have a conductor, the voltage is the same everywhere in a conductor. And so just in a wire, the voltage change between any 2 points in a wire is 0. And since it's acting like a wire, the voltage across it is 0. Okay, but now let's look at the transient circuit, which is the circuit where it hasn't gotten to be a wire yet, but it's also some time has started, so the current is changing. And it's from this transient that we get our time constant. And what is the time constant for an inductor? It is definitely one of those. Let's see. So if you mess it up, it is something you should definitely put on your formula sheet. Here we go. So the time constant for an inductor is L over R. L over R. So we have to get the resistance as seen by the inductor for this circuit. So when I look at this circuit, to get the resistance, I short out the voltage source. And I can see from the point of view of the inductor, the 30 ohm resistor and the 60 ohm resistor are in parallel. So our equivalent is 30 times 60 over 30 plus 60, or 1800 over 90, or 20 ohms. So our time constant is L.2 over 20. That's 2/10. 1 over 20. So our time constant is 1 over 100, and I'm going to leave it like that. So time constant is 1 over 100. Seconds, the units of a time constant are seconds. Okay, so I know the current at time t is the current at infinity plus the current at infinity minus the current at 0 times e to the minus t over tau. So I of t equals I at infinity, which was 0.4? What? 12 over 30. Did I do that right? Did anybody check me? Is that 0.4? Yeah, I think it's 0.4. E to the minus t over 1 over 100. I like to actually think of this as the formula, instead of the way it's written, I of t equals I at infinity plus I at infinity minus I at 0 times e to the negative t times 1 over tau, because then instead of having 1 over 100, I have 1 over 100, which is 100. So if tau is 1 over 100, thank you. It is. Yes, it is. It definitely is. I is 0, I, yes.
That's negative. Oh, no.
So it should be, because our initial current is decaying, so that's the one that should be in front. Wait, did I write it wrong in a bunch of places? 0 minus infinity, I did. So I wrote it wrong here. I guess maybe that's the only place. Okay, so 1 over tau is 100, so then this becomes I of t equals 0.4 plus or minus 0.4 e to the negative 100t. And is it amps? Do we have any milliamps or anything? No, just amps. So V of t V is L di dt. So L was 0.2, and then the derivative of this is 0 minus 0.4 e to the negative 100t times minus 100, or 0.2 times 40 e to the negative 100t is 8 e to the negative 100t volts.
So when we find tau, do we short out the voltage source every time?
To find the resistance, yes. So whether it's a capacitor or a resistor. So anytime you're looking for tau, so like let's say I had, this was my circuit. Let's be crazy and put a current source in there as well. Okay, so let's say this is my circuit and I wanted to find R. So for my time constant from the point of view of the capacitor. So I treat it like a Thevenin equivalence, and I'm going to short out my voltage sources and my current sources become open. And so this last part would not do anything because it's shorted, and these three would all be in parallel. I mean, it's open. Yeah. All right.